In this section, we're going to expand our discussion of rock deformation to include viscous deformation and plastic deformation, irrecoverable deformation. First, we're going to talk about viscoelastic behavior and the three manifestations of viscoelastic behavior. The first one, it's a type of deformation that we know, most of us know more or less well, because it's something that we commonly see in real life many times. And this is the type of deformation in which we apply a stress to an object, and even though we might keep the stress constant, the object is going to continue deforming with time. And will develop a deformation that not only depends on stress, but depends on time. This is something which is called a creep strain. And if we look at stresses and strains for this type of response, what we often see is similarly to what I was saying before. If I apply a stress as a function of time and I measure the strain, which is a result of that, I will see that as soon as I apply a stress, I would expect this solid to deform. This is the part of the elastic deformation. And if I were to keep the stress constant after some time, I would see that the solid continues deforming at a rate which is a function of time, and it is this creep strain that we mentioned before. In many rocks, this type of creep, it's also a permanent deformation, so it's actually not only viscoelastic, but also it's a viscoplastic. And an example application for this type of phenomenon is what we often see, for example, in salt formations, in which you drill a wellbore. Let me draw the cross section. Let's say that we drill a wellbore through a body of salt rock, and as soon as you drill the wellbore, you might have a stable cavity, but due to the external stresses that are applied on the wellbore is going to tend to close with time because of this creep strain. The hoop stresses applied on the wellbore wall are going to make it close in time. And depending on the properties of the rock, this will take more or less time. This is why sometimes some of these wellbores in salt rock, they have to be cased very quickly, because otherwise they close on the drilling string, and that's not good. Okay, another example that I have for this case is what we see, for example, when a fracture is closing. And let me move this a little bit up so we have more space here. Okay, so example number 2 is when you have a fracture with asperities that do not match each face on the two sides, and you apply a stress on such fracture with an irregular face. With time, you will see that these points that are subjected to high stress, because these are the ones that are actually carrying the load from each side to the other, this is going to deform on time, and the fracture is going to close, and your permeability is also going to be reduced in time, because of the action of these creep strains. Stresses may not be at the limit of failure, but still they are going to, the rock is going to deform with time. So this is what we call creep strain. Something very similar happens when you have the second type of phenomenon or second manifestation, which is number 2. And let me hold on to say exactly what that is. First, I'd like to introduce the physics. Okay, so let me recover my mouse. And one more. Okay. Let's say that now we do the opposite to what we did before. Instead of fixing a stress, we're going to fix the strain. And this is what would be called a strain controlled test or a strain controlled loading, in which we're going to fix a strain and we're going to measure a stress as a function of time. And let me add here this to make it clear. This is the action. This is the result, or what is measured as a result of that action. And in this case, we're going to subject the rock to a strain control test. And after, we're going to keep that strain constant. And let's say, for example, that this is going to be a compression. So the schematic for that would be having a rocky material and load it at the control strain, and then keeping that strain constant. So let's say, for example, that I do this type of loading in a load frame, and in the load frame I can control the displacement of the top and the bottom boundary. So this is similar to what we do, for example, with a Young modulus test, is that we vary this distance, and as a result we have a stress, and this is what gives me the Young modulus, stress and strain. But at some point I'm going to stop loading and I'm going to measure what happens with the stress. Can you guess what is going to happen? Let me increase this a little bit more. If after loading and after seeing that increase of stress, in this case compression in the vertical direction, we stop loading, if we are in the presence of a perfectly elastic material, then the stress should stay the same, because there is a unique relationship between strain and stress. However, in a visco-elasto-plastic material, we don't see that. What we do see is that after we keep the strain constant, the material is going to fail in very tiny increments inside at the microscopic scale, and the stress is not going to remain there at the top, but it is going to decrease with time. And this decrease with time is what is called stress relaxation. And it's a second type of manifestation for a viscoelasto-plastic material. And these two phenomena, creep and stress relaxation, are actually the two faces of the same coin. It's the same physics, it's just that the boundary conditions are different. What I impose in the creep strain is the constant stress, what I imposed for the stress relaxation is a constant strain. One gives me creep, the other one gives me stress relaxation. And an example of this is what happens. Let me invoke again the case of salt rock. Salt rocks, particularly, they develop a very significant visco-elasto-plastic response. So let's imagine that we are in a place in which we have a fault, and that fault happens to go through a salt formation. And let's assume that this is a normal fault. And if this is a normal fault, let me write it here. My horizontal stresses should be lower than my vertical stress. So what I would expect then in this case is that if I plot my stresses and pore pressure as a function of depth, I will have something like the following. Let's say that this is the vertical stress. It's just given by the overburden. And at the time of the formation of the fault, the formation happens so that the minimum horizontal stress, let me add the pore pressure first. Let's say that I have a hydrostatic pore pressure. The minimum horizontal stress is going to be dependent on the effective vertical stress, and the minimum effective horizontal stress is going to depend on the maximum stress anisotropy that this place can afford at these particular conditions. For the case of normal faulting, then that's going to be the limit. Let me write it over here. SH mean is going to depend on sigma H mean equal to 1 over Q sigma V, where Q is a function of the friction angle. And this number is more or less 3 for a friction angle equal to 30 degrees, which is very common in rocks and sediments. So that means that the lowest value of SH mean is going to depend on this distance being 1/3 of that distance, which is that equation. So at the time of fault formation, then this could be my minimum horizontal stress, even going through the salt. But what is going to happen is that because the salt doesn't like to have stresses which are different in different directions, so it's not going to like that sigma H mean is 1/3 of sigma B. With time, this formation is going to develop a deviatoric or anisotropy stress relaxation, so that this stress is going to tend to go and match the vertical stress, so that sigma H mean is equal to sigma B. Particularly in salts, this stress relaxation is very significant, so that the difference between stresses in any direction is going to eventually tend to 0. And this is what we would expect in such case. Okay, so this is a stress relaxation, and there is one more phenomenon which is a typical manifestation of visco-elastoplastic material. And this is something which is called stiffness dependency on strain rate, or strain rate stiffness dependency. Well, let me rephrase this. I think this is gonna sound better. Strain rate dependent stiffness. And what is happening in this case? Let's run a similar test to what we were doing before, and in which I am also going to deform this material, like for example in a typical Young modulus test, in which I'm going to deform the material a certain amount, and also that's going to depend on time. And in this case, this is what you will see. As we said before, if you have a perfect elastic material, then there is a unique relationship between stress and strain. So there is just one solution or one line possible for that phenomenon. However, with an elastoplastic material, what we see is that we have more than one solution. We may have one solution that could be the response for a slow strain rate. And what we will see is that if we perform the same test, but we do it faster with a faster loading rate, the Young modulus for the same material is going to be different. Where, of course, EFAS is going to be a higher than E slow. And this is going to be related to the variation of strain, and in this case, let's call it axial strain, with time, something which is called strain rate. Now, you could think that this is a physical phenomenon, that it's quite obscure and we might not pay much attention to it. But it is a phenomenon which is actually quite important, because in engineering applications, we usually have loading rates that vary quite a bit. For example, you could measure a Young modulus in the laboratory in what, 1 hour, maybe maximum 1 day. In that case, you are measuring a very fast Young modulus, not to mention if you are using elastic waves. However, in the field, you might have applications which are a lot slower than that. Like, for example, how long does it take to deplete a reservoir? It could take at least months, if not years, or more. So the times which are the times that play a role in this phenomenon, or how we measure a Young modulus and what we actually want to predict, can be quite different. And so it's going to be the difference between these two mechanical properties that I measure on the exact same material. And what happens, for example, when I consider what is the Young modulus of a rock over geological time, over millions of years? That's going to be even lower. And it is with the combination of this phenomenon of taking into account the viscoplasticity of rocks that, for example, we can explain a folded sandstone layer. You may go to the field and grab a piece of this rock. You test in the laboratory and has a very high Young modulus, and there will be no way to explain that you have a fault over geological time. However, we do see some of these faults, sometimes with some small fractures or faults, but sometimes without them. And these are only explained by the deformation over long times and by this reduced, you could call it a time average EM modulus that can explain that the rock is much softer and more ductile too over long times. There is one phenomenon that I like to mention in here. It's something that happens and facilitates this kind of deformation over long times is what is called subcritical fracture propagation. And let me write it over here. Well, let me write it over here because I don't want it to be confused with the lab. In subcritical fracture propagation, we have a propagation of a fracture which is slow with time, much slower than you would have if you exceed the toughness of the rock, and can facilitate propagation of fractures over long times, which facilitate the deformation of the rock and make actually the properties of the rock to change with time. And in that way, you can favor more displacements, more plastic and viscous displacements over time. And just to finish this example, let me also mention, well, probably I should have moved in order to make it match with what I was talking before. Let me move the geological scale example over here, and the field reservoir depletion example is also something that we have to consider, particularly in uncemented rocks like sands or mud rocks. If we have depletion of a reservoir over a long time, the YAM modulus that I expect, or in this case, the compressibility of the reservoir or the constraint modulus that I have in the field is going to be significantly smaller than the compressibility constraint modulus that I measured in the laboratory. Why? Because in the field, reservoir depletion is going to happen over several years, while in the laboratory, what I measure it's done over a few hours, or if not less. So these processes are quite different, and it's something that we should be aware of.